Good morning. My name is Daniel. I am a student at the University of Santa Maria. Today I will talk my work of the master. The title of this work is the short and long time scale variation of the 8 alpha double peak profile of the Pictor A galaxy. The galaxies are the big structure of the universe, composed of matter visible and matter not visible. For example, gas, dust, stars, planets, example, the dark matter. In some galaxies, it's possible to identify a presence of supermassive black hole. In some cases, have accreting matter. In this case, the galaxy is called the Active Nucleus or AGNs. AGNs is characterized from central compact source, the no thermal continuous emission in the spectral optical is identified intense lines in emission. Initially, AGNs were classified in two-layer groups. The type 1, the ray represents the broad and narrow line. Type 2, the ray represents the narrow line only. The figure in the left shows this case. These AGNs is characterized for different structures. These structures are the Supermassive Black Hole, the accretion disk, the broad line region, the toroidal structure, the narrow line region. In some cases, it's possible to identify relative jets. Some spectral optical, the AGN, is possible to identify the profile in two emission peaks. This phenomenon is caused through two regions. The first, ionizing source and recombination of hydrogen atoms with free electrons in the medium. In the second factor is the geometry and velocity distribution of the gas around the supermassive black hole. The figure shows one example of double peak profile, the NGC 1097. The line black shows the spectrum, the line red shows the double peak profile of this galaxy. This figure shows the spectrum, the galaxy major, the Galaxy Pictor A. This spectrum composes 18 observations over the 12 years. It's possible to identify significant variation when comparing observations separate for many years. For example, compare the spectrum, the 2006, and the spectrum 2012. In the bottom, the panel left, it's possible to identify significant variations in the form and the flux, the double peak profile. When combined, observation separate for months, it's possible to identify variation, but this variation is more weak. One focus of this work is measuring the double peak profile. For this, our group uses the software called the EFS Cube. The EFS Cube uses multiple Gaussians for fitting the spectrum. In this figure shows this process. With this fitting, it's possible to separate the flux, the double peak profile of the narrow line, the flux of the broad line. The broad line flux is a sum, the F red, F blue, the F sub C. F red is a flux, the side right. The F blue is a flux, the side left. The F sub C is the flux, the central, illustrated in green this figure. These measures help understand variation the flux in the side of the double peak profile. In this figure, show the light curve. This F red, F blue, F sub C. It's possible to identify variation more significant in the side blue, in the sequence the variation in the side red. In the F sub C don't have significant variation. It is spared this region, the disk, form this line, have low velocity in comparison the flux, the origin, the F blue, F red. In this figure, F brown illustrated the black, the purple is a sum, the F red and F blue. The measures the flux, the double peak profile, help understand the time-scale variation, the double peak profile. In this work, it's possible to identify two scales the variation. One long, when compared surveys separate for many years, for example, 2006, 2012, 2008, the red, F red, blue have different regions. The other scale identified in the study is the short time scale. The scale shows in the figure the bottom panel. There may be a variation the many months. Well, one objective of this work is understand the distribution of the matter around the supermassive black hole. For this, our group used the model called the saturated spiral model. This model has two components, the azimuthal component, the radial component. The azimuthal component has a form at the spot or a spiral arm. The region orange in the map shows this structure. Other component of this model is the component radial. This component is described by a radial maximum emissivity. The line dotted green shows this region, the maximum emissivity in the disk. This sphere shows one respect to the Galaxy Pictor A and the fitting using this model. This figure shows the fitting and modeling this disk in our observation the Galaxy Pictor A. This map help understand the chance to course in the disk is possible to identify rotation, the spot or spiral arm over the time, and chance the region, the maximum emissivity. When compared variation observed in the spectrum and observation spared from the model of the disk, the mass minimum for plan, the chance in the disk, are 2 times 10 AGT solar masses. The conclusion of this work is the data comprise the majority with the net data over 12 years. In this monitor, it's possible to identify 2 scale variation, one along the short time scale. In the work, we understand distribution of the matter. This variation is associated with the spiral arm and the rotation. In the shortest time scale are associated in farthest time scale of the light. In this accretion scenario, the mass minimum required for expected time scale variability, theoretically the disk, and the time scale observed in the spectrum is corresponding to mass 2 times 10 AGT solar masses. Thank you for your attention. I'll leave you this moment for questions.